Picture this. Right at this very moment, time is moving faster at the level of your head than it is at your feet. It sounds completely absurd, doesn't it? Yet this mind-bending reality is just one of the many astonishing consequences of a theory that forever transformed our understanding of the universe. This isn't science fiction. It's the remarkable world of Einstein's General Relativity. Today, we're about to embark on an extraordinary journey through one of the most revolutionary theories in the history of science. For centuries, humans gazed at the stars and believed they understood how gravity worked. Newton's laws seemed to explain everything perfectly, until Einstein came along and showed us that reality was far more fascinating than anyone had imagined. He didn't just change our understanding of gravity, he completely revolutionized our perception of the cosmos itself. What makes this theory particularly fascinating is how it reaches from the furthest corners of the universe right into our everyday lives. That GPS device you rely on to navigate through city streets? It would be hopelessly inaccurate without corrections based on Einstein's equations. The very same principles that help us understand black holes and the bending of starlight are actively at work in the technology you use every day. The implications of Einstein's work continue to ripple through modern science, leading to discoveries that would have seemed impossible just a few decades ago. We've now photographed actual black holes, detected gravitational waves from colliding neutron stars, and used gravity itself as a cosmic magnifying glass to peer deeper into the universe than ever before. If you've ever wondered how space and time can bend like fabric, or how we manage to capture an image of something so powerful that even light cannot escape its grasp, you're in for a treat. This journey through space-time will challenge your intuitions, expand your mind, and leave you with a profound appreciation for the elegant mathematics that describes our universe. As we delve into the curvature of space-time and explore its consequences, you'll discover that the reality we live in is far more remarkable than anything we could have invented. Throughout this exploration, we'll unravel the mysteries of warped space, dilated time, and the cosmic dance of massive objects. We'll see how a simple thought experiment about falling elevators led to one of the most profound scientific revolutions in human history. Most importantly, we'll discover how these seemingly abstract concepts have very real and measurable effects on our universe and our daily lives. So prepare yourself for a journey that will transform your understanding of reality itself. Whether you're a seasoned science enthusiast or just starting to explore the cosmos, this adventure through Einstein's universe promises to be an unforgettable experience that will change the way you think about space, time, and your place in the universe. To understand Einstein's revolutionary theory, let's start with a simple yet powerful visualization that has helped countless people grasp this complex concept. Imagine a large, taut sheet of elastic fabric stretched out horizontally. When you place a bowling ball in the center, it creates a depression in the fabric, warping its surface. Now, if you roll a marble near this depression, it will naturally follow a curved path around the bowling ball, potentially even orbiting it. This elegant demonstration illustrates one of Einstein's most profound insights. Gravity isn't a mysterious force reaching out through empty space, as Newton thought. It's the very curvature of space and time itself. But why did we need Einstein's new theory in the first place? Newton's laws of gravity had served us remarkably well for centuries. They could predict the motions of planets, help us launch satellites, and explain everything from falling apples to ocean tides. However, there were cracks in Newton's framework. The orbit of Mercury, for instance, displayed subtle irregularities that Newton's equations couldn't fully explain. More fundamentally, Newton's theory suggested that gravitational effects would be felt instantaneously across any distance, something that conflicted with Einstein's earlier discovery that nothing could travel faster than light. Einstein's revolutionary insight came from a profound reimagining of the nature of space and time. Instead of viewing them as separate, fixed backdrops against which events occur, he realized they were dynamic, intertwined aspects of a single entity, space-time. According to Einstein, massive objects don't simply exert a pulling force, they actually warp the fabric of space-time around them. Other objects then move along the straightest possible paths through this curved space-time, which we perceive as gravitational motion. Perhaps the most elegant way Einstein illustrated his theory was through his famous elevator thought experiment. Imagine you're in a sealed elevator in deep space. If the elevator accelerates upward at 9.8 meters per second squared, Earth's gravitational acceleration, you would feel a force pushing you down, identical to what you feel standing on Earth. Einstein realized this wasn't just a coincidence. It revealed a deep truth about the universe. There is no way to distinguish between gravitational effects and acceleration. This principle, known as the equivalence principle, became the cornerstone of general relativity. This revolutionary understanding had profound implications. If acceleration and gravity were equivalent, and acceleration could bend light paths, as Einstein showed, then gravity must also bend light. Furthermore, since gravity was now understood as curved space-time, time itself would flow differently in different gravitational fields. This explains our opening statement about time moving faster at your head than at your feet. Earth's gravity creates a measurable, though tiny, difference in the passage of time at different heights. Einstein's mathematics showed that mass and energy curve space-time in precise, predictable ways. The more massive an object, the more it warps the space-time around it. This warping affects everything: light, time, matter, leading to phenomena that would have seemed impossible under Newton's theory. Light bending around massive objects, time slowing down near strong gravitational fields, and even the existence of regions where space-time is so severely curved that nothing, not even light, can escape, what we now call black holes. The elevator thought experiment also revealed something profound about free fall. When objects are in free fall, they're actually following the natural geometry of curved space-time, what Einstein called a geodesic. This explains why astronauts feel weightless in orbit. They're not escaping gravity. They're falling along with their spacecraft in the curved space-time around Earth. This radical reconceptualization of gravity as curved space-time, rather than a force, marked one of the greatest intellectual achievements in human history. It not only solved existing problems in physics, but opened up entirely new areas of study and predicted phenomena that we're still discovering today. The theory's mathematical beauty and predictive power have made it one of the most thoroughly tested and confirmed theories in all of science, standing strong for over a century and continuing to reveal new insights about our universe. Einstein's general theory of relativity made three remarkable predictions that would ultimately transform our understanding of the universe. Each of these predictions, when confirmed, served as a powerful testament to the theory's accuracy and opened new frontiers in our exploration of the cosmos. Let's begin with the peculiar case of Mercury's orbit. For decades, astronomers had been puzzled by a subtle anomaly in Mercury's motion. The planet's orbit wasn't behaving exactly as Newton's laws predicted. Specifically, the point of Mercury's closest approach to the Sun, called its perihelion, was shifting slightly more than it should with each orbit. This tiny discrepancy, just 43 arc-seconds per century, had defied explanation for years. Leverrier, who had successfully predicted Neptune's existence from similar orbital anomalies, hypothesized that an undiscovered planet called Vulcan might be responsible. However, no such planet was ever found. Einstein's theory of general relativity elegantly explained this precession as a natural consequence of the Sun's warping of space-time. This was the first concrete evidence supporting Einstein's revolutionary theory. The second prediction was perhaps the most dramatic. Einstein claimed that light itself would bend as it passed near massive objects. This was a radical departure from Newton's theory, which treated light as immune to gravitational effects. The perfect opportunity to test this prediction came during the total solar eclipse of 1919. British astronomer Arthur Eddington led expeditions to Brazil and the island of Principe off the west coast of Africa to photograph stars visible near the edge of the eclipsed sun. By comparing these positions with photographs taken when the sun was not in the way, they could measure if and how much the starlight was deflected. The results confirmed Einstein's predictions exactly. Starlight was indeed bent by the sun's gravitational field by precisely the amount Einstein had calculated. When the London Times announced these findings with the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown," Einstein became an international celebrity overnight. The third prediction was perhaps the most elusive and took nearly a century to confirm: gravitational waves. Einstein proposed that accelerating massive objects would create ripples in the fabric of space-time itself, like waves spreading across a pond. These waves would carry energy and information about cosmic events across the universe. However, these ripples would be incredibly subtle. Even catastrophic cosmic events would create distortions smaller than the width of an atomic nucleus by the time they reached Earth. For decades, detecting these waves seemed impossible. Everything changed on September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory detected the first gravitational waves. The signal came from two black holes, each about 30 times the mass of our Sun, spiraling into each other and merging 1.3 billion light-years away. This detection not only confirmed Einstein's century-old prediction, but also inaugurated a new era of gravitational wave astronomy. Since then, LIGO and its partner observatory Virgo have detected dozens of cosmic collisions, including the spectacular merger of two neutron stars in 2017, which was also observed across the electromagnetic spectrum by traditional telescopes. Each of these predictions represented a profound departure from Newtonian physics and our intuitive understanding of the universe. Mercury's orbital dance showed us that space itself was curved. The bending of starlight demonstrated that even light, the fastest thing in the universe, follows the contours of warped space-time. And gravitational waves revealed that space-time isn't rigid but dynamic, rippling with the echoes of cosmic catastrophes. Of these three predictions, which do you find most astonishing? Is it the subtle shift in Mercury's orbit that revealed the curvature of space, the bending of starlight that made Einstein a household name, or the gravitational waves that let us listen to the universe's most violent events? As remarkable as these predictions were, they were just the beginning. Now, let's explore how these discoveries have revolutionized modern astrophysics and continue to shape our understanding of the cosmos. These confirmations didn't just validate Einstein's theory, they opened up entirely new ways of studying the universe. From using gravitational lensing to study dark matter to detecting binary black hole mergers through gravitational waves, these tools have become fundamental to modern astronomy. They remind us that the universe is not only stranger than we imagine, it's stranger than we can imagine. The impact of Einstein's general relativity on modern astrophysics has been nothing short of revolutionary, particularly in three key areas: black holes, gravitational lensing, and practical applications that affect our daily lives. Let's start with perhaps the most enigmatic objects in the universe, black holes. While Einstein himself was skeptical about their existence, they emerged naturally from his equations. The concept is both simple and profound. If you concentrate enough mass in a small enough space, the resulting gravitational field becomes so intense that nothing, not even light, can escape. This theoretical prediction remained in the realm of mathematics until 1971, when the first black hole candidate, Cygnus X1, was discovered. The culmination of black hole research came in 2019 with the first ever image of a black hole's shadow in the galaxy M87. This remarkable achievement by the Event Horizon Telescope collaboration showed us exactly what Einstein's equations predicted: a dark central region surrounded by a bright ring of light, with one side brighter than the other due to relativistic effects. The image of M87's supermassive black hole, weighing in at 6.5 billion solar masses, provided stunning visual confirmation of Einstein's theory. Black holes form through various processes. Stellar mass black holes are born when massive stars die in spectacular supernovae, while supermassive black holes, found at the centers of most galaxies, likely grew through a combination of mergers and by consuming vast amounts of matter over billions of years. We've now detected hundreds of black holes through their gravitational effects, X-ray emissions from their accretion disks, and gravitational waves from their collisions. Moving on to gravitational lensing, Einstein's theory predicted that massive objects would bend light like cosmic magnifying glasses. This effect was first confirmed during the 1919 solar eclipse, but its full potential wasn't realized until decades later. Today, gravitational lensing serves as one of our most powerful tools in astronomy. Massive galaxy clusters act as natural telescopes, magnifying distant galaxies that would otherwise be too faint to observe. This has allowed us to see some of the most distant and earliest galaxies in the universe, providing crucial insights into cosmic evolution. Perhaps most importantly, gravitational lensing has revolutionized our understanding of dark matter. By carefully mapping how light bends around galaxies and galaxy clusters, astronomers can determine the distribution of mass, even when it's invisible. These observations have provided some of the strongest evidence for the existence of dark matter and have helped map its distribution throughout the cosmos. The practical applications of general relativity extend far beyond astronomy. The global positioning system is perhaps the most widely used application of Einstein's theory in our daily lives. GPS satellites must account for both special and general relativistic effects. Time passes slightly faster for the satellites due to their distance from Earth's gravitational field, general relativity, and slightly slower due to their high orbital velocity, special relativity. Without these corrections, GPS would drift by about 11 kilometers per day, rendering it useless for navigation. Modern space missions also rely heavily on relativistic calculations. The precise navigation required for interplanetary missions must account for gravitational time dilation and the curvature of space-time. Looking to the future, proposed technologies like gravity assists and gravitational slingshots could potentially revolutionize space travel, allowing spacecraft to use the gravitational fields of planets and stars to achieve higher speeds with less fuel. Now let's engage our imagination for a moment. Try to visualize the curvature of space in 4 dimensions. While we can't directly see it, we can understand it through its effects, much like we can't see the wind, but can see its impact on leaves and trees. Think about how space and time are woven together and how massive objects create dips in this cosmic fabric. And consider what it would be like to live near a black hole, where time dilation becomes extreme. If you were to orbit a black hole at a safe distance, you might experience time passing at half the rate of Earth time. You could watch a year pass on Earth in what feels like 6 months to you. This isn't science fiction, it's the reality of Einstein's universe. The implications of general relativity continue to unfold, from detecting gravitational waves to understanding the large-scale structure of the universe, from improving satellite navigation to planning future space missions. Einstein's theory remains at the forefront of both pure science and practical applications. As we push the boundaries of exploration, both on Earth and in space, general relativity continues to guide our understanding and technological advancement, proving itself to be one of the most profound and practical scientific theories ever developed. General relativity didn't just change our understanding of gravity, it gave us the tools to unravel the story of the universe itself, from its explosive birth to its possible ultimate fate. What began as Einstein's insights into gravity has blossomed into a cosmic narrative more magnificent than anyone could have imagined. When Einstein first applied his equations to the universe as a whole, he was so startled by what they suggested, an expanding universe, that he added a cosmological constant to keep the universe static. Years later, when Edwin Hubble discovered that galaxies were indeed moving away from each other, Einstein called this adjustment his greatest blunder. His original equations had predicted the expansion of the universe before anyone had observed it. This revelation was just the beginning. Working backwards from this expansion, scientists realized that the universe must have been smaller, denser, and hotter in the past. Following this logic to its ultimate conclusion led to the Big Bang theory, the idea that our entire observable universe emerged from an incredibly dense, hot state about 13.8 billion years ago. General relativity provides the mathematical framework that allows us to trace cosmic history back to mere fractions of a second after this moment of creation. But the theory's implications stretch far beyond the past and into the future. By measuring the current expansion rate of the universe and the distribution of matter and energy within it, we can use general relativity to project possible futures for our cosmos. Will the universe continue expanding forever, growing ever colder and darker in a big freeze? Will it eventually collapse back in on itself in a big crunch? Or will dark energy, represented by Einstein's once discarded cosmological constant, drive an ever-accelerating expansion? These questions, once purely philosophical, can now be approached scientifically thanks to Einstein's theory. However, there's a frontier where general relativity reaches its limits, the quantum realm. While general relativity perfectly describes gravity at large scales, it breaks down when trying to describe phenomena at the smallest scales, where quantum mechanics reigns supreme. This incompatibility becomes particularly apparent when studying black holes or attempting to understand the first instant of the Big Bang. This has led to one of the greatest challenges in modern physics, the quest for quantum gravity, a theory that would unite Einstein's description of gravity with quantum mechanics. String theory, loop quantum gravity, and other approaches attempt to bridge this gap, suggesting exotic possibilities like extra dimensions, microscopic vibrating strings, or space itself being quantized into discrete units at the smallest scales. The search for this unified theory has revealed surprising connections. For instance, through the holographic principle, theorists have discovered that gravity in one universe might be equivalent to quantum physics in a universe with one fewer dimension, a mind-bending concept that emerged from studying black hole entropy. These investigations suggest that space, time, and gravity might be emergent phenomena arising from more fundamental quantum processes we're only beginning to understand. The climactic realization is that general relativity, while incredibly successful, is likely not the final word on gravity. Just as Newton's theory was encompassed by Einstein's more complete description, general relativity may ultimately be absorbed into an even more comprehensive framework. This doesn't diminish Einstein's achievement. Rather, it highlights how his insights continue to guide us toward ever deeper understanding. As we stand at this frontier, we face questions that would have been unimaginable before Einstein. What is the quantum nature of space and time? Are there other universes? Did time itself begin with the Big Bang, or did something exist before? These questions arise directly from pushing Einstein's theory to its limits, showing how a simple theory about gravity has led us to contemplate the deepest mysteries of existence. The stage is set for the next revolution in physics. While we don't yet know what form it will take, we can be certain that Einstein's insights will be crucial to finding it. Just as general relativity revealed the large-scale structure and history of our universe, perhaps quantum gravity will finally illuminate the ultimate nature of space, time, and reality itself. The beauty of Einstein's theory lies not just in its mathematical elegance or its cosmic implications, but in how it touches our everyday lives in ways both profound and practical. While we may not notice it, general relativity influences our world every time we use our smartphones for navigation, take a plane flight, or simply check the time. Perhaps the most tangible example of relativity in our daily lives is GPS technology. Every time you use your phone to navigate to a new restaurant or track your morning run, you're relying on precise timing from satellites that must account for relativistic effects. Without these corrections, your location would be off by kilometers within a single day. This same technology helps coordinate global shipping, enables emergency responders to find people in need, and even helps farmers practice precision agriculture. What began as abstract mathematics has become woven into the fabric of modern civilization. But relativity's impact on our lives goes beyond technology. Einstein's theory fundamentally changed how we understand time itself. The realization that time is not absolute, but relative to motion and gravity, has profound implications for how we view our place in the cosmos. When we look up at the stars, we're not just seeing across vast distances. We're looking back in time, seeing light that left those stars years, centuries, or even millennia ago. This perspective gives us a unique appreciation for our cosmic context and the interconnectedness of space and time. Einstein's legacy extends far beyond his scientific contributions. He showed us that the most fundamental aspects of reality, space, time, gravity, could be questioned and reimagined. His work demonstrates how pure thought and mathematical reasoning can unlock deep truths about the universe. This legacy of bold thinking and willingness to challenge established ideas continues to inspire scientists, philosophers, and dreamers across all fields of human endeavor. Moreover, Einstein's own life story, as a patent clerk who revolutionized physics through thought experiments and mathematical insight, reminds us that groundbreaking ideas can come from anywhere. His later years as a public intellectual and advocate for peace show how scientific understanding can inform moral and social perspectives. Einstein demonstrated that a scientist could also be a humanitarian, using their platform to advocate for social justice and international cooperation. The ongoing search to understand the cosmos that Einstein helped initiate has yielded practical benefits beyond anything he could have imagined. Technologies developed for space exploration and astronomical observation have found applications in medical imaging, materials science, and computing. The need to share and analyze vast amounts of astronomical data has driven developments in international scientific cooperation and information technology. This pursuit of cosmic understanding also serves a deeper human need. Throughout history, humans have looked to the stars to understand their place in the universe. Einstein's theory gave us new ways to ask these ancient questions. When we see images of distant galaxies, detect gravitational waves from colliding black holes, or contemplate the Big Bang, we're participating in humanity's grand project of self-discovery. Today, as we face global challenges like climate change and sustainable development, the lessons of general relativity remain relevant. Einstein showed us that apparently separate phenomena, space, time, matter, and energy, are deeply interconnected. This holistic perspective reminds us that our actions have far-reaching consequences and that solutions to complex problems often require us to think beyond our immediate experience. The theory also highlights the importance of international scientific cooperation. Modern astronomy and physics require global networks of telescopes, detectors, and researchers working together across borders and cultures. This model of international collaboration in pursuit of knowledge offers hope for addressing other global challenges. As we continue to explore Einstein's universe, new questions arise. Dark matter, dark energy, and quantum gravity present mysteries that may require revolutionary new ideas to solve. But Einstein's example shows us that such breakthroughs are possible through careful reasoning, bold imagination, and dedication to understanding nature's deepest truths. In the end, general relativity reminds us that we are part of something vastly larger than ourselves, a cosmos whose mysteries continue to unfold. As we use Einstein's insights to navigate our daily lives and probe the furthest reaches of space and time, we honor his legacy by maintaining that sense of wonder about the universe and our place within it. The theory not only changed our understanding of the physical world, but also expanded our sense of what's possible through human creativity and reason. As we conclude our journey through Einstein's revolutionary theory, we're left with a profound appreciation for how radically our understanding of the universe has changed in the past century. Einstein showed us that the cosmos is far stranger and more wonderful than anyone had imagined. Space bends, time flows at different rates, black holes puncture the fabric of space-time, and gravitational waves ripple through the cosmos, carrying messages of catastrophic events. The universe revealed by general relativity is not the clockwork mechanism of Newton, but a dynamic, interconnected web where space, time, matter, and energy engage in an eternal cosmic dance. This reality challenges our most basic intuitions about the nature of existence. We've learned that our common-sense notions about time being absolute, space being flat, and gravity being a force must be abandoned in favor of deeper, more fundamental truths. Perhaps the most important lesson from Einstein's revolution is that our everyday experiences can be misleading when we try to understand the fundamental nature of reality. The fact that time moves more slowly in stronger gravitational fields isn't something we can easily perceive in our daily lives. Yet this effect must be accounted for in the GPS satellites that guide our cars and phones. The notion that massive objects warp the fabric of space itself seems absurd to our earthbound intuitions. Yet we can now photograph this very effect around black holes. Einstein's legacy teaches us that the pursuit of truth sometimes requires us to think beyond our immediate experiences and trust in the language of mathematics and careful reasoning. His work reminds us that the universe doesn't conform to our expectations. Rather, we must conform our thinking to the universe as it actually is, however strange that might seem. Today, as we face new mysteries like dark energy, dark matter, and the quantum nature of gravity, Einstein's approach continues to guide us. These phenomena may seem as counterintuitive to us as curved space-time did to Einstein's contemporaries. Yet by following the mathematics and evidence wherever they lead, we continue to push the boundaries of human knowledge. The journey of discovery that Einstein began continues. Each answer we find leads to new questions. Each insight reveals new mysteries. From the quantum realm to the cosmic web, from the interiors of black holes to the first moments of the Big Bang, we are still exploring the implications of his revolutionary ideas. If you're as fascinated by these cosmic mysteries as we are and want to continue exploring the wonders of the universe, join us again next week here on Exploring the Universe. We'll be diving deep into how supermassive black holes, those cosmic monsters predicted by Einstein's equations, actually shape the evolution of entire galaxies. From the smallest quantum fluctuations to the largest structures in the cosmos, there's always more to discover about our extraordinary universe. Don't forget to like this video and share it with friends who share your fascination with the cosmos. Subscribe to our channel and hit the notification bell to ensure you don't miss any of our upcoming explorations of space, time, and the fundamental nature of reality. Together, we'll continue to unravel the mysteries of Einstein's universe and beyond. Remember, in the words of Einstein himself, the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. Thank you for joining us on this journey through space-time, and we'll see you next week for more cosmic adventures.